be a little nausea-inducing, I'm sure. So welcome to NANOG 74 here in Vancouver. It's pretty good to be here, right? I don't know if all of you agree with me, but I'm kind of a foodie, and I think those who know me well will agree that Vancouver, I think, has some of the best Japanese food anywhere in North America. So if you're so inclined, I would highly recommend that you follow the Ryan Donnelly diet and eat nothing but ramen and sushi for the next 3 days. And the only thing that I will say about that is that it's guaranteed to be delicious. So, moving on, here we are. I was looking back and I realized that we actually haven't had a NANOG in Canada in 3 years. Like, last time I think was Montreal. And we have not been in Vancouver in over 6. So it's great to be back, right? The weather's doing great things for us, while we're here, welcoming us back in proper Pacific Northwest fashion. We have over 900 of you here. There are 264 members, 9 students, 21 college immersion participants, and 224 first-timers. I think that's a pretty good turnout, right? So how about an applause for that? Yeah. Now, before we go any further, there's a very important message that I have from Billy Idol regarding the weather. So please, it's October. It's Vancouver. It's the Pacific Northwest. Bring a light sweater wherever you go, and probably an umbrella too. Yesterday we had a hackathon, and while I was not there, the feedback that I've had is incredibly positive. I heard it went really well, so thank you to Oracle and to Sudo for sponsoring. I think it's a great addition to our program. Could I get a show of hands for those that were there? And good? Yeah? I'll take that as a yes. Okay. As you guys have heard me say before many times, we have a great cadre of sponsors sitting alongside us, helping us put these programs on. We think of these folks like family. They're there alongside us. They've been through thick and thin with us, various stages of organizational growth, various initiatives, various funding levels, and they've stood steadfastly by our side. So let's get a big round of applause for our sponsors. We quite literally could not do this without you, so thank you very much. Now, since this is the last time you're going to hear from me as board chair, what I thought I would do is take a few minutes, in keeping in mind that I know you guys like short openings, but talk about what it means to be a part of something. And by that I mean being a member of NANOG. You see, we have an election going on right now, and we have a slate of great candidates. We have a set of bylaw initiatives on the ballot, and then I looked at our turnout for last October. 28.6% of the members voted. 28%. I don't know how else to say this, so I'm just going to say it. That isn't good enough. We need more from you as members. Could I get a show of hands for all the members in the room? How many folks are you here? Okay, so this message is for you. We need more. This is a room full of brilliant people, experienced people. Everyone has their own lens on what they want the organization to be and what they've seen it turn into. We want your perspective in deciding how this organization is governed and the kinds of initiatives we want to take on. So we need your voice, we need your time. Please take a minute, get educated, and vote. There's really no such thing as not voting, right? There's just the scenario in which you amplify the voice of the person next to you. I'm the kind of person that's voted in every state and federal US election since I turned 18. It's just who I am. And it's the kind of turnout and the kind of dedication that I would ask of our members as well. So, becoming a member, what does it mean? It means you get an express registration lines, it means you get discounts on registration, it means you get the ability to vote, and it means you get a bunch of special considerations in every meeting. So these are all really, really good things and you want them. So please, for those of you that haven't become members, join us. Add your voice to the chorus. We need your input, we need your expertise. We want your thoughts on how we transform this organization. If you look at the ballot, you will see the list of bylaw changes that we're proposing for your consideration this time around is large. Please be thoughtful, please engage, please look at them, please read them, ask us questions. We want all that input. And as I mentioned, we have a fantastic group of people that are on the ballot running for the board. There's 2 seats that are vacant, mine and Dave Temkin's. Get to know them, talk to them, ask them questions, and actually next up, one of the board candidates, the current PC chair, Mr. Ryan Woolley, is going to take it over from here. So thank you very much, and have a great NANOG.
All right, thank you, Ryan. As Ryan mentioned, I'm Ryan Woolley. I'm the current PC chair. So I get the pleasure this time of giving you the rundown of the network diagram. So thanks to TELUS for the 1 gig of transit. You might be able to see that, but that terminates into an Arista 7280 QR and some layer 2 beyond that. So that's your internet access while you're here. Okay, quick notes on the program. We have, I think, a really great program this time. We have 27 presentations. Again, all these submissions are solicited by the PC in some cases or submitted to the PC, but all of them are reviewed. On average, about 10 people get a chance to look at and provide comments on each of the publications that you're about to see. Nothing here is paid placement. There are 20 folks who are appointed by the board to perform this function. And PC is self-governing. If you have any questions on the PC roles, there's appointments will be not this NANOG, but after the following NANOG. You can look for the folks with the blue badges that say committee, and feel free to ask us any questions. A couple highlights on the talks that we have. Shortly after me, we'll be starting off with a keynote from Paul Barford of University of Wisconsin. He had a paper that was widely published in the media on climate change risks to internet infrastructure, so he'll be opening. That'll be an excellent talk. Many of you know Richard Steenbergen, who has presented on optical networking in the past. He'll be talking about the economics of optical networks as well. We brought back the security track. That's tomorrow morning, and we have a number of speakers. The focus is BGP route security this time. On Wednesday afternoon, we have a number of talks related to telemetry and NetFlow that we've grouped together, so I think that's very topical for many people and probably worth checking out. A couple notes on the microphones. You'll see throughout the room microphones. After the presenter has finished speaking, and if there is time remaining for questions and you have a question for the speaker, just go ahead and walk up to the microphone, wait to be acknowledged by the speaker, introduce yourself, provide your name and your affiliation, and please remain at the microphone long enough for the speaker to finish answering your question. Please also note that NANOG has an attendance charter. The details are available on the website, but briefly, please treat everyone respectfully. Realize that your behavior reflects on you, on your organization, your affiliate / employer, and on NANOG as a whole. We have lightning talks. They'll be presented on Tuesday and Wednesday, so if you have an idea for a lightning talk, which is about a 10-minute presentation, you can submit that today or tomorrow for either the Tuesday or Wednesday slots. The program committee will vote to accept the 3 best talks for each of those. The agenda is available online in Guidebook. There's a webcast URL if you want to follow along if you need to step away. And almost all of the presentation materials will be available from the agenda as links in case you want to take a look at them later. You are right now in regions C through F. We'll have general sessions here for most of this, as well as beer and gear, for a slightly larger environment since that's a pretty popular event. Region C foyer just outside will have breaks and espresso, and A and B around the corner will have breakfast and lunch. Tuesday social is at the Harbor Event Center. Please fill out your surveys. We ask this of you every time and try and remind you between sessions, but this is the primary mechanism by which the staff, the board, and the program committee get to know what you like and what you didn't like. So please take a minute to fill those out. We actually do read them, and they do make a difference in the quality of the presentation. You also have a chance to win these fantastic prizes that are presented here. So an additional incentive for you, aside from having an even better NANOG program, is you can win some of these gifts. All right, that's all I had. I think we finished up a little bit early, so we'll be back at 10:30 with our keynote presentation. You can hang tight until then. Thanks.
Good morning, everyone. So, welcome again to NANOG 74. Since we got a little bit of time, let's get a chance for everyone kind of just to stand up and kind of say hello to your neighbor, greet one another. In these conferences, we sit in desks and chairs all day long, and we kind of don't move around. So, take a moment to just say hello to the person next to you. Come on, don't be shy.
Hi, folks. All right, let's get started, please. All right, I'd like to introduce our first presenter for this morning, our keynote speaker. Welcome to Paul Barford of the University of Wisconsin, who will be talking about Lights Out, Climate Change Risk to Internet Infrastructure.
All right, up and down. Thank you very much. It's a pleasure to be here to talk to this group. First of all, my thanks to the organizing committee for the kind invitation to come and speak today. As an academic, I'm always quite pleased when I get a chance to present technical findings to a group of practitioners who have the background and experience of this group. So I'm hopeful that the ideas and findings that I present today will generate some thoughts that you have, and I'll look forward to speaking with you afterwards about any issues that you're interested in or potential ways in which we can move this study forward in the future. So let me start out with first of all, the statement that I am absolutely a climate change skeptic. I'm a person who deals with data regularly. I guess at some level I'm a data scientist. I've looked at the data related to climate change, and I think that things are actually much worse than is generally being reported in the media. I'd like to say that I came up with this saying myself, but I actually have to attribute it to my colleague at Caltech, John Doyle, who I've been talking about with these issues for some time. So let me start out by saying that climate change is the most significant issue that mankind is facing. When I wrote up this deck of slides some time ago, and my wife took a look at it, she said, "You mean except for the current president of the United States?" I said, "Well, okay." And so I'll say that it's the most significant long-term issue that is facing mankind. And in general, the objectives of our work are to simply acknowledge the risk that we're facing and to assess it quantitatively with respect to impact on communication infrastructure. So risk is the first aspect of our study. Secondarily, given the risks, to assess the impact or potential impact on communication infrastructure. And then finally, given the assessment of potential impact, to understand where and how we might be able to mitigate the effects. So that's the sort of the thumbnail of our grand strategy for addressing these issues. And what I'm going to talk about today is specifically this initial study on risk assessment. So for the rest of the time that I have to speak today, I'm going to give a thumbnail overview on a very complex issue, which is the issue of climate change. I'm going to assume that pretty much everyone in the room has heard about this at some level. Some people are perhaps experts and know more than I do. But in general, when I have conversations with people about this, it's sort of a good idea to level set, and that's what we'll do in the first part of the talk. The second part will focus on the approach that we've taken for risk assessment, and then finally I'll present the results of our study and talk about where we're going from here. So let's start out with the definition of climate change. What do we actually mean by this? What it refers to are shifts in worldwide weather phenomena associated with the increased global average temperatures attributed largely to human activity over the past century. Okay, so this is a crisp statement of what we mean when we say climate change. And it's important to understand that from the perspective of climate scientists, and we have a climate scientist who has been involved in our study so far, happens to be my wife. She runs a climate science lab at the University of Wisconsin. The fact is that the scientific evidence for this is unequivocal. There is no dispute, despite what you might read in papers about various people in a couple of institutions who think otherwise. So what do we mean by unequivocal? Well, the fact of the matter is that over the eons, there have absolutely been cycles in issues related to climate change, in particular, the amount of carbon dioxide in the atmosphere. We can track this through polar ice cores and come up with compelling quantization of these effects. And what you can see from this graph is over the past 400,000 years, we absolutely have cycles. However, in the last century, what we've seen is basically a spike that goes well beyond anything that has ever been seen historically, at least in the record that we have shown here. And this is where much of the concern is generated from. This is a graph that I copied from the NASA page. And there is a wonderful breadth of material that's associated with this on the page. So I direct you to that if you'd like a broad overview. So what are we talking about specifically? What we're talking about specifically is the fact that carbon dioxide is a greenhouse gas, meaning that when it's emitted into the atmosphere, it has this effect of trapping heat. And the result of the CO2 sequestration in the atmosphere is that global temperatures go up. So some of you might have seen the recent article in the New York Times, a very nice interactive piece on how temperatures have gone up in your hometown. So if you haven't seen it, take a look at it. And what they basically show is how over the last 30 or so years, the average temperatures or temperatures over 90 degrees, the days over 90 degrees have gone up rather dramatically in most locations across the United States. There are other effects beyond simply temperature rise. For example, extreme weather events being more common. For example, sea level rise, which is what we'll talk about today. And then of even more concern, perhaps, are the secondary effects that could be much more significant. Things like food security, right? Because of the changes in weather pattern, it's possible that areas that are currently sort of the breadbaskets of the world could experience droughts or other catastrophes that make them unable to produce food in the quantities that are required. And the shit does hit the fan when people are hungry. Certainly there are issues related to loss of property. There was a wonderful article in The Guardian several weeks ago about migration patterns in the US and the impending migration away from coastal areas in the United States to inland areas in the United States. And then we have further issues for those of us who care about animals and the environment, such as habitat loss. So these are all important impacts of this basic starting point of increases in CO2 in the atmosphere because of human activity. So it's one thing to see it in text. It's another thing to see it in pictures or in person. Probably some people here live in California. California fires were devastating this year. Of course, there have always been fires in California, but the prediction is that the spread and scope of fires is likely to increase. We have local flooding events that are on the rise. In Wisconsin, we've had devastating floods this year, significant damage to infrastructure around the state, and obviously it's not localized to Wisconsin, but elsewhere, and then of course, the possibility of extreme events, extreme thunderstorms, and hurricanes like Florence recently. I'd be fascinated to talk to anyone in the room who's had to deal with the aftermath of Florence. I imagine that it's been significant with respect to impact on communication infrastructure, and love to get your insights on that. And then, of course, the issue at hand is sea level rise. Anybody here from Florida? Anybody live in Florida? One or two people. If you've been to Miami, you know that sea level rise is real. I remember going to South Beach and other areas in Miami 20, 30, 40, lots of years ago, and the issues were not present. The ocean was off in the distance at the end of the beach, and now we have these events where it routinely comes into streets and other areas, so we know that this is not something that is being made up. And in fact, other companies, like insurance companies, recognize this and are taking proactive steps to try to deal with these issues. So the research question at hand is, what is the risk of sea level rise to internet infrastructure? This is the specific issue that we're addressing in our study. And what this requires then is for us to define a couple of things. What do we mean by internet infrastructure? This is the first question that people ask me, and now I'm speaking to a group that probably knows more about internet infrastructure than any other group in the world. So first of all, what we mean are the physical links that carry communication data traffic around the world. And when we embarked on this study, I felt like I knew something about physical links, and as I went along, I certainly learned a lot more. So, when you drive down the road and you pass a utility truck that has a big spool of either orange or yellow conduit, and you kind of slow your bike down, or maybe as you're walking along, you speed up to take a close look, what you see is inside that 2-inch or that 4-inch piece of conduit, there is all sorts of stuff, right? Could be smaller conduits, could be a single smaller conduit, and then if you look really, really closely, what you can see is there are some small bundles of fiber. And when you start to dig into this in detail to see how these conduits are actually manufactured, what you see, not surprisingly, is that there are a broad range of conduits and construction methods and ways in which the actual fiber bundles might be threaded through those conduits. In any case, that is the physical link component that we're talking about. And then, of course, when it comes to actually deploying these, they're deployed in a variety of ways, typically along public right-of-ways of some kind, using some kind of trencher. As you see on the left side of the screen here, trenches are typically deployed between 18 inches and 36 inches, okay? And when I first started doing this study, I thought, oh, well, they must be actually deployed in some kind of other conduit somewhere or something. And in fact, no, they're just trenches dug in the ground. The conduit is put into the ground, and then the trench is covered up for long, long stretches. Okay, so that's our terrestrial fiber. Then we have this other whole world of fiber, the submarine fiber, which is way, way, way more interesting than the fiber that's deployed on land. Okay, so these are the cables that obviously provide communication capability that connect continents. And investigating this aspect of connectivity was really an eye-opener for me. First of all, there are dramatic differences between the hardening of the actual conduit versus the conduits that are deployed in the ground. We have a much larger amount of protective material to keep seawater out that surrounds a lot of armor. And way in the inside of this, what you have are the little fiber strands that actually carry the communication information. As these cables are deployed near land, underwater, they're actually trenched and thick. And then as we get into the open ocean, where it's very, very deep, the cables are typically pulled along the seafloor and are not buried and are much thinner. And the amount of technology that's gone into this in terms of transmitting these fibers or transmitting signals in these fibers over these vast distances underwater is amazing. And of course, it is the case that these are perhaps the most weather-resistant materials that we have with respect to physical infrastructure. So this is the first aspect of internet infrastructure. The second aspect are the nodes. These are the places where these conduits come up above ground, where they interconnect with each other. And the ways in which we have these nodes deployed is sort of equally varied, right? Very broad range. So anybody from Great Britain in here? One or two people, you probably recognize the green box. right? So these are the little internet cabinets that you see all over Britain. I laugh when I see these whenever I'm in Britain because they usually have big signs on them that says, "Internet is here," which you don't really see in the United States or elsewhere. I love the fact that the Brits are proud of their communication infrastructure. I can't help but think back when I was 17 years old. If I would have seen something like that, I would have gone, "Oh, interesting." Anyway, you take it from there, right? We've got some other kooky things going on about times when people were 17 back in the United States right now, so I'm just going to leave it at that. In any case, we start out with things that are very small, right? And I would contend not particularly resilient to extreme events or to things like inundation in the upper left-hand corner. And then as you move around clockwise, we get to a Google Fiber hut, and we get to a submarine cable landing facility, and then we get to, in the lower left-hand corner, a large exchange point. And the point of all of this is that we, again, have a wide variety of these geographic locations and associated infrastructure where cables come together. All right, so in terms of how we assess this research question, what are the risks now that we've established what it is that we're trying to understand what might be at risk? What we're doing is scientifically something that's very, very simple. We're just doing a geographic overlap analysis. We're looking at where physical infrastructure is deployed and how projected sea level rise might flow over that. Okay? So what this requires is a capability that we used a geographic information system for, namely to assess this overlap. And the only real technical challenge in that regard was to make sure that we had very precise alignment between the two different GIS formats, one for the representation of internet infrastructure and the other for the sea level rise projections. To further understand the issue of risk, we developed a simple metric to quantify this, the coastal infrastructure risk metric. I'll talk about that a little bit more later in the paper. To conduct the study, the basis for our study were infrastructure maps that we have assembled as part of our Internet Atlas project. I'm going to talk about that in more detail. And then we utilized the data sets from the U.S. National Oceanographic and Atmospheric Association, NOAA, which are very detailed. In particular, the Office of Coastal Management publishes these maps. They're openly available, and you should go to the site if you're interested. Host of materials on sea level rise from NOAA. All right, so we're going to talk about the data assets first. Our Internet Atlas project has been going on at University of Wisconsin for almost 8 years now. This is a project that has now assembled what I believe is the largest repository of maps of physical infrastructure in the world. We've assembled this data through search. There are lots of online materials that are available if you know how to search correctly. I gave a talk on this at NANOG a couple of years ago. And in addition to the repository, we make aspects of this repository available through a web portal. I'll give a URL for that at the end of the talk. The portal, it's hard to deal with data, so we take the step of making the data able to be visualized and analyzed in certain ways. That's what the portal is all about. So we have over 1,500 maps in the repository today. Thanks to all of you who have made the maps available online or either through communication. Importantly, all of the maps that we have are geocoded to the best of our ability to do that, meaning precise locations for nodes and links to again, the extent that we can do that. And then we've added additional functionality in the portal beyond simply the ability to visualize and utilize maps by making certain measurement capability available. And then embedded is the ability to take advantage of certain algorithmic and analytical capabilities in ArcGIS. So Just a little bit of a sort of background, more background on Internet Atlas. Again, thanks to you for making these maps available, or to your salespeople who believe that they will be able to be more effective by being able to show maps of your infrastructure to potential customers. One of the things that I've noticed over the years is that maybe as a result of some of the work that I've done or other people have done, some of these maps have changed. So level 3 CenturyLink people, the level 3 CenturyLink map is on the right-hand side, second from the top. That map is no longer available, so I missed that. Used to be one of the best maps that we had, but thanks to the Zio guys for still keeping their map up and running, at least the last time that I looked. In any case, exact geographic locations are difficult to come by. So what we've done in Internet Atlas is understand that if we don't have a precise mapping for a piece of internet infrastructure, so as you can see in some of the cases, there are maps that don't. They just give squiggly lines or perhaps a straight line. Based on our prior studies, what we've done is to associate that with existing infrastructure like road and rail as an attempt to give it geographic accuracy. So we've done our best, but one of the things that I want to be clear about is that we do not contend that we have ground truth for all of these networks. We've done the best that we can with what we've got. I believe that we're highly conservative in what we've done. Namely, if we have a link or a node and we just have no idea where it is, we leave it out. So all of the analyses that we've done for our risk study have excluded certain pieces of infrastructure where we don't believe that we have high confidence or where we don't have high confidence. All right, so if you go to the Internet Atlas portal, you can request credentials for Internet Atlas through the DHS Predict program. What you see is, first of all, a very zoomed out view of the internet and its associated infrastructure. And what a geographic information system allows you to do is to navigate through this to take advantage of other data sets that might have, for example, topographical information, that might have road and rail information, that might have census information, right? Lots and lots of entities use GIS as the basis for understanding, manipulating, and analyzing their data. So we take advantage of that built-in capability. So a zoomed-in view, a little bit more zoomed-in view, relates to the metro fiber maps that we have in Atlas. So we have around 200 metro fiber maps, and of course when you're looking at this you can see some long-haul links. Yes, I overlaid some of the long-haul links over some of the metro fiber links just to give context. Some of you probably recognize your own networks in here, and of course this is a zoomed out view. But to the extent that we can, what we've done is we've gone through and geocoded down to the street level. We don't make street level maps available to anyone at the request of our friends at DHS. So we're very careful about that. We have developed technology for obfuscating maps. So when we distribute them, we can fuzz these things just a little bit. Actually, we can fuzz them in exactly whatever way that we want. We can move things randomly by meters. We can move things randomly by miles. So we're sensitive about security issues. And the idea is that with this repository, we can address research questions that otherwise we couldn't address. One of the research questions that we addressed that I talked about the last time I was here was identifying long-haul fiber. So this is the map that we produced, right? So we stated the definition of long-haul, meaning links that span at least 30 miles that connect cities that have a certain population level. And what we were able to distill from that was a map that had 273 nodes, about 542 conduits that span the United States, and we were able to do certain analyses on that long-haul graph to assess risk and opportunities to improve performance, and I'll give a citation for this study at the end of the talk. All right, so we're going to shift gears. That's the Atlas data set. That's what we utilize in order to understand where internet physical infrastructure is. We consider both links and nodes that we've been able to glean from public search. The other data set that we take advantage of, which you are probably less familiar with, is the sea level rise inundation map from NOAA. Sea level rise inundation is really interesting when you drill down on it from a scientific perspective. These are NOAA's projections of sea level rise scenarios in coastal counties in the US over the next 100 years, okay? So it's important to know that these projections are based on constructive models that begin first of all with projections of the amount of CO2 that will be emitted into the atmosphere. That's the starting point. So when we look over this 100-year time scale, the starting point says, well, how much CO2, how much additional CO2 is going to go into the atmosphere? Then what are the corresponding impacts in terms of heat rise, of temperature rise? And then what are the corresponding results in terms of things like glacier melt and other aspects, polar ice cap melts, that lead to rising sea levels. And in particular, with respect to making projections on how the sea is going to inundate coastal areas, they have very interesting and very precise maps about geographic features in these areas. They look at tidal activity, they look at other hydrological features, and they have built these so-called bathtub models that then look at how the sea will come into certain areas. Okay? So these are not done in any way other than a very, very careful scientific methods. And indeed, when it comes to the projections themselves, they don't offer a single projection. They offer a variety of projections based on things like whether or not we might take steps to reduce CO2, right? For example, through alternative energy sources or other means of conservation. And what they provide then are a range of scenarios that they link to GIS databases so that we can do the kinds of things that we're doing. And indeed, we follow their guidance. We use the highest mean rise ratio, which projects rise basically over 6 feet in the next 100 years. Actually, between the time that we did the study and now, these highest mean rise scenarios have actually been increased. So the story is not better, it's worse over the last year. So keep that in mind when you look at the results that we'll present. So what does sea level rise mean for the internet? Well, so one of the things that I had to look into and educate myself a little bit about was whether or not it mattered that cable and conduit infrastructure that was buried under the ground would be impacted by suddenly being underwater, okay? So I found this very nice white paper by folks at Datwyler. Anybody from Datwyler here? All right, well, take a look at their white paper. It simply looks, if you just go to their white papers, it's like, I don't know, the 6th or 8th white paper down, the effects of water on fiber cable. And the fact is that water is a threat to fiber infrastructure. People can say, hey, wait a minute, there's no electricity going through there. Yeah, I know, but there are still issues with respect to the fact that these infrastructures were made to be weather resistant and not waterproof. And anybody who's done any plumbing understands that there's a difference between sort of getting there and actually making things so that they don't drip, right? So for the plumbers in the room, maybe there's some nods. I've tried to do it. I love that white tape that you put on things so that it doesn't drip, right? It's hard. And the fact is that we have infrastructure deployments that are very old, right? And whenever you have aging, you have cracks that start to form, and you have the possibility then for water actually getting into things that it wasn't meant to get into. And while we can't quantify the specific risk of breakage, that's not an objective of our study. What we can say is that things that were not designed to be underwater all the time are now going to be underwater or surrounded by water, and that's the risk that we're talking about. Okay, so what we're looking at then is overlap of infrastructure and projected sea level rise, right? And we're doing this with our GIS system. To quantify this, we create a simple metric, which we call coastal infrastructure risk metric. This is an attempt to give us a means for being able to compare and contrast different areas. We look then at these different temporal scenarios that are offered by the NOAA models, and we implement this all in our ArcGIS infrastructure. Particular to our risk metric, we're using the kernel density estimator. Kernel density estimation is a non-parametric means for estimating probability density function. So we're looking then at particular areas. So we outline a geographic area, let's say the Miami metropolitan area. We look at the amount of infrastructure that exists in that area. Then we look at the amount of inundation that's supposed to take place in that area. And we're doing an estimation then at the density of infrastructure that will be underwater. That's what our quantification and coastal infrastructure risk metric is all about. So what's the outcome? Well, here it is in terms of number of nodes. And I shouldn't have used the word affected. What I should have said is the number of nodes that are at risk. And what we find is that when we break nodes down into the different categories as indicated from our source data, what we find is what's shown in the graphic here, that approximately, or almost 800 POPs, 235 data centers are going to actually be affected by 1 foot rise. What do we mean by affected? What we mean is that they'll be surrounded by water, okay? So if you don't consider that to be an impact or an effect, then that's up to you. I would contend that that would probably be something that would be concerning. What's most interesting about this graph and the next one is that the difference between what happens in 15 years in 2030 and what happens in 100 years in 2100 is not that much different, okay? Meaning that and it's not sort of surprising at all, we've deployed all of this infrastructure next to the coast because that's where people live. People like living next to water, okay? And now what's happening is the water is going to surround in the case of POPs, or cover in the case of conduits, the infrastructure that's shown in the graph. And it's not going to be so much worse 100 years from now, but I think that the take-home message from this is we need to pay attention to this sooner rather than later. Likewise, on fiber conduit miles. Now, let's be clear, what we can't do is we can't quantify the actual fiber strand miles because we don't know the details of strands in the conduits. So what our study shows is the number of conduit miles that are going to be affected, impacted, at risk, however you want to interpret it, basically underwater. And again, the take-home message here is that much or most of it will be underwater in 15 years rather than 100 years. So if we care about that, and I would contend that this is an even more significant issue than the issue of POPs or nodes, then we should address it sooner rather than later. All right, so one of the fun things about GIS is that we can create some interesting pictures. So in this case, we have a map of Manhattan on the left, a map of Miami on the right. The green area is the area that will be above water in 100 years. The blue area is the area that will be underwater in 100 years. And while it's hard to tell because it just looks like a bunch of sort of little spider webs on here, all of the dark green is internet infrastructure. So anything that's in the blue is underwater. In the case of Miami, what we see on the right, the red are actually the submarine cables and their associated landing points. So where those cables are underwater now, not a concern because they're already underwater, but the landing points are all implicated in sea level rise. Okay, so in the paper then, we also break out in terms of details, the numbers of POPs, data centers, IXPs, and landing stations that will be the nodes that will be surrounded by seawater in the next 100 years. So here's the breakdown. Probably not too surprising for people in the room who have so much operational experience with these areas. Likewise, we break out in terms of long haul, given our definition of long haul and metro fiber to the extent that we have representation in our database, the areas that will have the most fiber conduit miles underwater, and the percentage versus the overall percentage. And again, you know, the sort of the standard culprits are on this list. And then the final breakdown are the infrastructure providers that have the most infrastructure at risk in terms of either fiber conduits that will be underwater or nodes that will be surrounded by water. So this relates very much to our kernel density function. So for example, I hate to admit it, but I'd never heard of broad sky before, right? So I went back to my co-author Ram over and over and over again and said, you know, have we got this risk metric right? It doesn't surprise me that CenturyLink or AT&T would be represented highly in this graph. They have the most at risk because they have the most infrastructure, right? They've got huge deployments across the country and across the world. But what's up with this broad sky? Well, it turns out that they have some interesting, basically POP-level infrastructure in certain parts of the country. And based on how we calculate our risk metric with this kernel density function, because of the fact that they have dense deployments in these areas, the estimation winds up elevating them in terms of our rankings. So in some sense, this is a little bit of an artifact of the way that we're calculating this metric. All right, well, to summarize then, climate change has lots of implications. Sea level rise, severe storms, fires, floods, kind of bad, stuff that we need to care about. So the focus of this initial study, and I want to emphasize this is an initial study. It's for US only. We haven't considered the world. It's for a single threat, sea level rise. We haven't looked at any other aspects of climate change. We've done an assessment of risk, and the way that we've done it is to fuse two data sets, our Internet Atlas data set with the NOAA sea level rise inundation data. And the overall findings is that we've got around 4,000 miles of conduits and whatever the associated strand miles are with those. Around 1,000 colo centers that will be either underwater or surrounded by water in the next 15 years. And the fact is that the amount of additional infrastructure that will be implicated doesn't change that much given the current inundation models that we have available. So there's much to do on this, and this is part of the reason that I'm excited to be here with this group today, because even though we've done this initial study, which highlights these risks or implications of sea level rise, we have to take next steps with this. All right, so the first thing that we need to do is expand our risk assessment beyond the United States. Obviously, we've got a lot of infrastructure in the US, but I know that there's representation from other folks in the room. One of the anecdotes that my co-author Ram relayed from his presentation on this in another forum was that some folks from a Dutch ISP, is there anybody from Holland in here? Anyway, the Dutch folks said, yeah, we're all over this stuff. You know, obviously the Dutch have had to deal with seawater for hundreds of years, and they're perhaps the most facile in understanding how to do everything in an area that is always at risk with seawater inundation. And the fellow that he was talking with said that they have indeed taken significant steps to harden their infrastructure and to deploy in different ways to ensure that they have waterproofness as opposed to weather resistance in their cabling and in locations where the cables come above ground. So we could perhaps learn something from the Dutch. We obviously need to expand the scope of threats. We've only considered a single threat. I'd be interested in anyone's experience, for example, with the California fires being in the general vicinity of San Francisco. I wondered whether there were any implications with respect to those fires. Obviously, if you've got heat at the level that I understand was experienced in those fires, for anything other than cabling that would be very deeply deployed underground, there would be heat implications. For anything above ground, I'm sure it's gone. So I think fire threats, and then obviously severe storms, right? We experience these periodically in the US. Climate change says that we're going to experience more. Obviously, again, we experience severe weather, hurricanes, cyclones, and so forth in other parts of the world. So ways in which we can prepare not just for the aftermath of the storms, but to actually harden infrastructure in anticipation of the storms. I would love to learn from you about that. Once we understand risks, then we need to assess possible impacts. These are things like how can we route around these catastrophes? What are the potential secondary or tertiary effects of outages in particular areas? What happens if a submarine landing station is completely inundated with water? Obviously, those locations are hardened against storms. I don't expect the buildings to collapse. But what happens if they're underwater for extended periods of time, right? When they can't get power or when their backup power goes down. What are the potential implications there? Those are the things that we need to assess. And then, as I said at the beginning, one of the things after we've assessed impacts is to understand whether there are ways that we can actually mitigate these effects, because the sea level rise in all likelihood is not going to go away. We're going to have populations move inland, and that probably suggests then that additional infrastructure to support that population move is going to be required. And we need to understand then where and how we can begin planning for those kinds of changes. All right, well, that concludes my talk. I think I'm actually reasonably on time here. So I'd like to acknowledge my co-authors, Ram and my wife, Carol. The associated references can be found on my publications page. You can just do a search for that, and I'm sure you'll find it. So I referred, first of all, to the paper that this talk is based on that was published last July, and then the long-haul infrastructure paper is also available on my website. If you're interested in Internet Atlas, there is a URL to the portal, so take a look. If you're interested, what you'll only see is a very high-level summary view, but you'll get kind of a picture when you click on the Visualize link. If you want to get more details, I'll be happy to give accounts to people. You'll have to request them through the DHS Impact portal. It's simply a process of registration, and then we'll pass that along, and again, would love to engage with you on these ideas more generally. Thank you for your attention.
Hi, passing on a question from someone who's remote, Sandra Murphy of Parsons. Sandra asks if understands that the data that you have is actually a part of the Impact program, and that Impact is scheduled to cease operations in December of 2018 due to lack of funding. And she wonders if there's going to be any impact on the ability to look at the data that you mentioned that was available through Predict.
No impact. And by the way, thank you for asking that question, because I do want to make clear that the actual coastal infrastructure data set, we are going to make that, and in fact, I have it right now, we will make that available officially through Impact. So that's a data set separate from Atlas that I'll be happy to make available as a shapefile for people, right, if you want to reproduce the results of this study.
Right.
Hi, Nick Carlin from Microsoft. This is very near and dear to my work. So comment on the observation of the 100-year sea level rise. It's much bigger than just network infrastructure. I mean, in that I analyzed that same NOAA data and was looking at the impact in the Bay Area, and at 6-foot sea level rise, Google is also entirely underwater.
That's great.
And I'm very happy to see people looking at this, but I think there are actually kind of some bigger immediate risks from natural disasters that we're not looking at. And one thing that I think both the risk industry and network people kind of fail to look at is like joint probability of impact and how that actually impacts the redundancy of our network. There are some modeling systems like the OASIS loss modeling framework, which are very good at doing that type of stuff. So.
Yeah, I couldn't agree with you more, and thank you for pointing out that understanding impact, right? So assessing the impacts of these risks, that's the thing that we're thinking about right now, the thing that we're actually working on right now. So it's easy for us to extend our study to other parts of the world to the extent, again, that we have representation in our data sets. But I think that this issue of impact is very significant. We don't have good models for understanding that, right? I mean, I've been hedging and hedging and hedging about, what is the impact of having a closet surrounded by water versus a landing station surrounded by water. Well, I don't know. What we need to do is we need to create models that give us a sense for what the range of potential impact might be, right? And then what we can do is we can work with folks like you to assess the validity of those models and then to assess the implications of what the impact might be. So we need to expand this. I love the observation about what's going to happen in the Bay Area over the next 100 years, and I appreciate your comments. Thank you.
Well, thank you. Ovidio Viorica, State of New Mexico. I have a simple solution. Move to New Mexico.
So look at the Guardian article. I'm pretty sure that was highlighted as a potential destination.
Were you able to put a number next to this estimated risk? People always care about the associated cost.
No. It totally makes sense. By the way, just as a related aside, we actually went back and forth about the title for this paper. Some people think it's alarmist to have an exclamation point in a title of a research paper. Oh, it's alarmist. Or by including the word climate change in the title of the paper, we're ringing an alarm bell. And you know what the answer is? Yes, we're ringing an alarm bell. We're trying to ring it loud because we want people to pay attention to this. And things like highlighting potential costs is an important additional aspect that we haven't been able to do, just again because we haven't looked at that impact issue. All we're doing is assessing risk at this point, and once we get to the point where we can assess potential impact, then costs are a consequence of that. Okay, thank you very much. Thanks.
Thank you, Paul. To introduce our next speaker, Amir Sheikh from AT&T Labs.
Thank you, Ryan. I'm Aman Sheikh. I'm from AT&T. Now, if you see me a little bit nervous, the reason is because I saw AT&T as number 3 in that list of providers that are at risk. So it has nothing to do with this presentation. In any case, I'm going to talk about virtualized PE for layer 3 VPN service using open source software. Let me get started by stating our objective. Our objective was to demonstrate feasibility of creating a layer 3 VPN VPE using open source software. And feasibility is a key word here. We are primarily focused on showing that one can create a VPE using open source software for layer 3 VPNs. There are other aspects of creating a VPE or using a VPE, such as performance, robustness, advanced features, and we are not focusing on those in this particular talk. So then the next question is, why the hell do we want to create a VPE? Our first motivation was to create a use case for AT&T's DNOS, which is the disaggregated network operating system. AT&T has published a white paper related to DNOS, and release is imminent at the end of the year. So that was our first motivation. The other motivation for actually having a layer 3 VPN VPE as use case is based on 3 keywords in there: L3 VPN, VPE, and open source software. L3 VPN is a service I'm sure all of you are probably familiar with. This is a service that service providers like AT&T can provide on a shared backbone, where they can create an illusion of virtual private network for lots of different customers. And I'm sure if you are an enterprise or if you are any kind of business, you probably connect to a service provider and access this service in order to connect your different sites which might be geographically distributed. So this is a widely used service. Why VPE? Well, it turns out that VPE is a key VNF for this service. This is the network function that sits at the edge of the service provider network and connects to the customers. And when the traffic comes from the customer or goes out to the customer, this VNF is what acts as an entry point and an exit point for the traffic. And finally, open source software, and I don't think I need to say much about that. The open source software allows increased agility in rolling out new features, programmability, etc. And so these were our reasons for trying out this experiment. And as we expected, we faced numerous challenges. The open source software that we decided to use didn't run as is. It didn't just use out of the box from day one. We had to make some enhancements which were related to functionality, as well as putting these software pieces together. So there were enhancements that we had to do related to integration as well. And as we go along, there will be details about these things in my presentation. So here are the software components that we used in our open source VPE. For the control plane, we used 2 softwares. One is called FRR, free range routing. And in particular, we used OSPF, LDP, and Zebra components from FRR. And then the second software that we used is called GoBGP. And as the name implies, we use GoBGP for its BGP functionality. As for data plane, we chose AT&T Viata's DPDK based data plane. And together with the control plane that I just described, that's what forms the Denos use case VPE. But in addition to AT&T's data plane, we also verified feasibility with just pure Linux data plane. So essentially packet forwarding using Linux kernel. And we also used VPP data plane. In particular, it's release 1801, plus some modifications to the router plugin, which allows VPP to communicate with the control plane. This is a picture of what the VPE looks like. Both the control plane and Viata DPDK data plane actually run in Linux user plane as Linux user plane processes. In particular, in control plane, we have GoBGP, FRR OSPF, and FRR LDP running as separate processes. All these processes learn routes from their neighbors. They select their best routes, and then they install these routes down into FRR Zebra, which runs as another process. FRR Zebra in this particular case communicates with AT&T Viata Route Broker, which is a scalable and reliable platform for RIB management. And the route broker in turn programs the FIB for the Viata's data plane. The routes can also be pushed to Linux kernel forwarding table. So in fact, when we replace the Viata's DPDK data plane with pure Linux, the route broker and the Viata FIB go away, and the FRR Zebra process directly communicates or installs route into Linux forwarding table. When we use VPP, what happens is that VPP again runs as a user plane data process, just like Viata DPDK data plane. But instead of communicating with route broker, it syncs its routes with the Linux kernel forwarding table. Okay? So this is what the picture looks like of the test bed that we used for verifying feasibility. In the middle is a service provider. I bet this is the smallest service provider that any of you have seen in your life. It has only 3 routers, 2 PEs which are interconnected by a core router. And the core router doubles up as the VPN v4 route reflector as well. Inside the core we use OSPF and LDP for connectivity between VPEs. Now this service provider in this testbed provides connectivity to 2 customers, blue and red, and each customer has 2 sites, on the west and on the east. So you can see that VPE west is connected to west offices of both the customers, and similarly VPE east is connected to 2 offices, offices of the 2 customers. And with this setup, in order to verify feasibility, what we do is we run video stream for each customer from its video server on the right all the way down to its video client on the left. And similarly, we do the same thing for the red customer. So these video streams are run concurrently when we do our verification. Not only that, the other thing that I would like to point out is that both the video servers have the same IP address, and similarly both the clients also have the same IP address. And this is to show that when you use VPN, customers are free to choose their IP address assignments. And in this particular case, they have this situation where they are using the same IP address, and even with that, VPE is able to keep the traffic segregated across the customers. So despite using same IP addresses and running the video streams concurrently, the VPE is able to do what is expected of it in terms of providing L3 VPN service. Now I wish I could show you the videos, but unfortunately I cannot. So what I did is the next best thing, which is to capture packets when we did one of our feasibility and or rather when we did one of our verification testing. And this is a snapshot of packets that were flowing through the core router, which is sitting in the middle. And in particular, we captured packets that were coming from VPE East into the core router. So this is the interface that's facing VPE East on the core router. And over here, what I've done is I have highlighted 4 packets. The first one is going from red server to the red client. And the thing that you need to note here is, and I don't know how well it is visible, but you will see that this is a packet that has 2 MPLS labels. The outermost label is for the loopback of VPE West, which is the egress for traffic going to the client. And the inner label 145 corresponds to the red VRF on VPE West. The next packet, the second packet, is going in the other direction. So this is the packet that's going from client to the server. And this packet, if you note, only has a single MPLS label. And this label corresponds to the red VRF. Now the reason that this packet has only a single label is because it is captured at the interface towards VPE East. So the core router does what is known as penultimate hop popping, which is removing the outer label for VPE East before the packet is sent out. And that's the reason why you're seeing only a single label in this particular case. Similarly, the third packet is going from blue client to blue server. And again, you see a single label, which is 144, which corresponds to the blue VRF on VPE East. And the last packet is again going in the other direction from blue server to blue client, and you can see 2 MPLS labels, the outermost being the label for VPE West, and the innermost label is for the blue VRF. Okay. So next, what I'm going to do is go through the configuration details, in particular how we configured our testbed to verify feasibility. And I have divided the configuration into 2 parts. The first part is about establishing LSP or label switched connectivity between PEs within the service provider network. And then the second part deals with enabling L3 VPN service on top of the LSPs established within the service provider network. Before I go into the details of configurations, let me mention that we use 2 loopback addresses on every box running in the service provider network. In particular, the first loopback, which I call loopback 1, is used for IP traffic, especially the control plane traffic related to OSPF, LDP, and BGP. The second loopback is used for MPLS traffic, and so all the customer traffic for the VPN customers uses loopback 2 or is bound to loopback 2 of the boxes in service provider network. So this first slide shows how you enable MPLS forwarding on Linux itself. So these are the set of commands that we need to run on every box to enable MPLS forwarding. Here I am showing them for VPE East, but similar commands were run on the other 2 boxes. So the first command is to enable IPv4 forwarding. The second command is to enable MPLS modules. The third command actually enables MPLS forwarding on the particular interface, in this case the interface facing the core router. And the last command is to allocate space for the MPLS label table. So once you run these 4 set of commands, the box can act as an MPLS forwarder. But of course, you need to program the box. And in order to do that, as I mentioned, we run FRR, OSPF, and LDP processes on all the 3 boxes within the service provider network. On the left, you see OSPF configuration for VPE East. On the right, you see configuration for LDP on VPE East. And it's fairly standard. I mean, if you have done OSPF and LDP configuration, this will look very familiar. You configure router ID for OSPF, add both the loopbacks to the OSPF, and you enable adjacency to the core router, in this case, within the OSPF configuration. On the LDP, again, you see router ID configuration, and then you specify the interface over which you want to enable neighbor discovery. So in case of LDP, instead of specifying neighbor explicitly, we ask LDP daemon to discover neighbor automatically, and that's what the configuration over here shows you. So once this configuration is in place and once OSPF and LDP processes are running along with Zebra, the service provider network has label switch paths enabled within itself. So now you can ping from one PE to another, you can reach them, there is connectivity between these PEs. So now we are going to move on to enabling layer 3 VPN service. The first thing we are going to do is enable VRFs or VRFs on the Linux box at the Linux level. So what we are doing, again, this is on VPE East, and similar things were done on VPE West. So on VPE East, the first set of commands create blue VRF as a link or as a device and brings it up. The next command, the fourth command on the screen, adds the interface facing the VCE to the VRF. So in this particular case, this is the interface facing VCE blue East, and that's added to VRF blue. And the last set of commands are interesting. This allows BGP process running on VPE East to listen on port 179 on VRF bound interfaces. Without running this command, what happens is that the BGP process listens on port 179 as it usually does, but it only listens on those interfaces which are bound to the default routing table or default forwarding table. In order to make BGP process listen to port 179 on VRF bound interface, we have to run these 2 syscontrol commands on Linux CLI. This is the BGP configuration on VCE. For VCEs, we used FRR BGP daemon, and you can see the configuration over here. The second line, which I have highlighted in the configuration, allows configuration of the session to PE's loopback as opposed to the interface facing the VCE. The rest of the configuration again is fairly straightforward. You have router ID. We then enable or we add those networks related to video server to BGP process. And finally, the 2 set of commands enable peering session with VPE East. Next is the Go BGP configuration on VPE East. three key points here. The first key point is that in order to use next hop self, which is basically assigning the next hop as the loopback of its own interface, we had to use an export policy. So as routes come in and go into the service provider network, this policy attaches the loopback 2 of VPE East to the routes as next hop. The second box here shows how we communicate with Linux kernel and via data plane via FRR Zebra. And the last set of commands show how IBGP session is established with the route reflector. This slide has details of how the next self policy works. So at the top is the set of routers for which we want to apply the export policy. And in this particular case, the route reflectors is the only router that we care about in our small ISP over here. And then the next set of commands show that when routes go to the core router, you attach loopback 2 of this PE as the next hop before sending the routes out. So this is how the next hop self policy is realized in GoBGP configuration. The last bit is about configuring WRF and eBGP neighbor. Now ideally I would have liked to configure them using GoBGP configuration file, but the GoBGP version that we were using didn't allow WRF configuration. So we had to rely on GoBGP CLI to do the WRF configuration. And you can see that the first command adds blue WRF along with its route distinguisher and route target, and the next command adds the neighbor session and attaches it to the blue WRF. This is GoBGP configuration for route reflector. Again on route reflector, which is co-located with the core router, we use GoBGP as our BGP process. The configuration is fairly standard. You configure AS number, router ID, etc. And then there is the session, IBGP session for VPE East. And similarly, there is another session configured for IPE West. One thing I'd like to point out is that there is no communication happening with FRR Zebra here, because the only routes that this route reflector learns and distributes are VPN v4 routes, and these routes do not need to be pushed down to the forwarding table, because core router only switches packets based on MPLS labels and not VPN v4 prefixes. So that was all about configuration. Next I am going to talk a little bit about implementation, and in particular I would like to talk about L3 VPN support in GoBGP. As far as implementation goes, there are two key aspects. Number one is what I call key building blocks. This is essentially the machinery that you require to be able to do layer 3 VPN in GoBGP. So things like internet routing with BGP is a necessity. The other aspect that we require is able to partition routing table into a global table and WRF specific tables. We need support for VPN v4 and v6 address families like IP prefixes, route distinguishers, and MPLS labels. And finally, we require support for route targets, which allows us to associate routes with VRFs. Now, as far as these building blocks are concerned, GoBGP had everything that we wanted, so we could use them straight away out of the box. But then there is the second key aspect, which I call interaction with outside world. So things like configuring VRFs. So this is where a user configures WRFs and associates an eBGP session with GoBGP. Then the second aspect is about handling routes received from a CE, similarly routes received from route reflector or remote PEs, and finally communication with Zebra. So these four aspects, which are about interacting with outside world, this is where there were some pieces that were missing in GoBGP, and we had to do some enhancements to the code to make them work. Okay? So let me go through the details of those enhancements. This is the case where GoBGP handles a route received from an adjacent CE. The CE over here is on the left side, VPE is in the center, and the route reflector is on the right side. So let's see what happens when VCE sends a route. Note that this route for prefix P is a pure IPv4 route, and this is what customers usually send to service providers. Now let's see what happens with this route. Let's say that this route is installed in the blue verf as it should, because the session is associated with the blue verf. And then when BGP runs its decision process and installs this route into FRR Zebra and into the fib, this was the place where things didn't work correctly with GoBGP. And this is where we had to do some enhancements to GoBGP to make this work. Okay? Now the route is also imported into the global table, and this is the place where the IP prefix is turned into a VPN v4 prefix by attaching a blue specific route distinguisher and blue MPLS label. This part worked fine, except that we had to do an enhancement for attaching MPLS label with the route. And then finally, this route is sent out to the route reflector for distribution to other PEs. And in our case, it will be the other PE, the second PE. The communication part or the sending of the route worked fine, and we didn't have to make any modifications to GoBGP in this particular case. So as far as handling routes received from an adjacent CE is concerned, we had to make two modifications. One was how the route is installed into FRR Zebra, and the other is how MPLS label is attached to the route. Or in particular, we had to make sure that the correct label is attached to the route before it is imported into global table. Now on this slide, I am showing how GoBGP handles route when it comes from route reflector. So these are the routes that are coming from the other PEs. So let's see what happens when a route reflector sends a route. Note that the route is a VPN v4 route, so it has route distinguisher and MPLS label attached to it. This route is first put into global routing table by GoBGP. Everything good so far. Now what GoBGP does is something curious. It actually pushes this route down to the Zebra daemon, and then Zebra will install the VPN v4 route into the forwarding table. This is not a deal breaker, but it's not something that is required. And in particular, if there are 100 or millions of routes, this can actually lead to scalability concerns. So what we did is we disabled the part where GoBGP actually pushes the route down to FRR Zebra so that it doesn't go down into the forwarding table. The route is then imported into blue verf, and when it is imported, the route distinguisher is removed and the route essentially becomes an MPLS labeled IPv4 route. So the blue label is still associated with the route. And then eventually this route, after it goes through the route selection process, needs to be installed into the RIB and down into the forwarding table. And again, here we had to make some enhancement to make sure that the route was installed into the verb forwarding table with correct label. So as far as, let me finish this. And so after that, the route is sent as a pure IPv4 route to the VCE. So as far as this scenario is concerned, where the route comes from route reflector, again we had to do two modifications, and both had to do with how routes are communicated down to the Zebra daemon. So this brings me to my last slide. So in summary, what we demonstrated was that we could indeed create a layer 3 VPN VPE using open source software. In particular, we used two softwares for control plane, GoBGP and FRR. And in case of FRR, we ended up using OSPF, LDP, and Zebra daemons of FRR. For data plane, we used three distinct data planes. One is AT&T's Viata data plane, which is DPDK based. But we also verified feasibility with VPP and pure Linux forwarding planes. This required us to make enhancements to GoBGP, so things didn't work as is straight out of the box. In particular, we had to make modifications which required, which dealt with how routes are installed into forwarding table, how MPLS labels are assigned to VP and V4 routes, etc. And if you are interested in more details, or if you are interested in the modified code, it's available on GitHub. There is a URL there. And there is also a URL for DANOS, or Disaggregated Network Operating System, if you are interested in learning more about it. And with that, in fact, I finished fairly early, so there is ample time for questions. Thank you. Any questions?
Michael Sinatra, ESN. I think I completely missed it. I like the idea of using GoBGP, but I'm not sure why you didn't just use the FRR BGP daemon instead brought in GoBGP. Was it scalability, or was it something else?
No, that's a good question. So when we started this project, it was last year, sometime around this time last year, and at that time FRR did not have support for VP and V4 at all. And that was the reason why we went ahead with GoBGP. Now what has happened is that in the meantime, I think sometime this year, FRR has started adding support for VP and V4. And we in fact tried it out in our test bed, so the VP and V4 part works fine. The place where we had some trouble was again the policy for setting the next hop to its own loopback address. But in near future, we are again going to try out FRR.
Thanks.
Any other questions?
And request and exam solutions. From your presentations, I saw what in the initial state, the daemon that was expected to perform MPLS function was able to do VRFs, but was not able to do basic label operations like exporting labeled routes to proper tables and exchange routes with route reflector, and also install route into proper routing table. Mm-hmm. So it looks like it didn't have capability to work with MPLS at all, but only like VRF Lite support. Is it correct, or is it something?
Yeah, so I think you are referring to this slide?
Yes.
Yeah, so you're mostly correct. What happened is that GoBGP had MPLS support, but what it was not doing was it wasn't attaching MPLS labels to the routes. So when the routes went out to route reflector, they went out as VP and V4 routes, but the label was always initialized to 0.
But
okay.
So initially with daemon is designed to operate only in VRF Lite mode, it turns out, right?
I suppose, but I'm not 100% sure with VRF Lite whether you need MPLS labels or not. Yeah. But in this particular case, we needed MPLS labels.
Yeah.
And so the routes had a place for MPLS label, but they were always initialized to 0. So in fact, I can show you something which is in the backup. Yeah, this slide. So when we configure the VRF, now with the change, what happens is that forget about this part, but once the VRF is configured, GoBGP contacts FRR Zebra and obtains a label and associates it with the with the specific VRF that you are trying to configure. And this is the label then, which is then propagated along with the route to the route reflector. Does that make it clear?
Yeah, I just was wondering how it was expected to operate without this functionality. So
I don't know. So that's where I think, I don't know how many people had actually tried to do VPN, layer 3 VPN with GoBGP. I have no idea. And then when we tried, we ran into some of these problems. In fact, when we tried it first, we could only get basic internet connectivity to work. And there were all these issues which prevented us from doing a full-fledged layer 3 VPN.
So it looks like that you just brought the necessary functionality to this daemon. So
Right.
Thank you.
Yeah, sure. Any other questions? I guess we can then have early lunch. Thank you so much.
All right, thank you. We'll break for 2 lunches. There's a newcomer's lunch and lunch for everyone else, and return to this room at 1:30 to continue. Thanks.